To understand about static electricity, let us consider two bodies A and B which are charged. I'll say A is positively charged, so I will denote it with plus sign. And B is negatively charged, so I will denote it with a negative symbols over there. So whenever I say there is a positively charged, it has an area surrounding it where it can influence it. There is a much similarity between magnetism and electricity when we try to study about static electricity. You know, when you take a magnet, there are two poles, north pole and south pole. Okay. So the north pole in magnetism is analogous to the positive charge in static electricity. And similarly, the south pole in magnetism is analogous to the negative charges in static electricity. Okay. Whenever I place a north pole or south pole, these two poles are not separable. Okay. In magnetism, it is not separable. That means a magnet will have definitely a north pole and south pole. I cannot have separately a north pole or separately a south pole. So when I take a magnet, it has a region surrounding it where its influence can be felt. And what we call that? That is a magnetic field. Okay. Similarly, when we come to static electricity, charged bodies, each charged body will have surrounding it a region where we can feel the effect of it. That field, that region, we'll call it as electric field. Okay. So there is some region surrounding it where we can feel the effect of it. Suppose I take one more positively charged body here. Okay. Then this charged body will be repelled by this charged body because both are identical charges. In magnetism, you know, two north poles will repel and two south poles will repel. Okay. Same way here in static electricity, we will have two like charged bodies repel. It can be a positive charged body, another one be a positive charged body. That means a positively charged body will repel another positively charged body. Similarly, a negatively charged body will repel another negatively charged body. Two unlike charges will get attracted. So a positively charged body will always attract a negatively charged body. Right? Now here, this is a positively charged body A. What's happening is, it is having a surrounding some region where we can feel the influence of it. So that field, that region, will call it as the electric field. Okay. So this is the electric field. I am just writing a boundary over here, assuming that this is the boundary of the electric field for this charged body A. In that boundary, within that region, that means within the electric field of this charged body A, if I place one more charged body, a small charged body, a small charge. For a small charge, we can assume that it will be a point charge. Okay, that means whenever I say a point charge, it means to a charge which is very, very small in magnitude. Okay, now when I place this, what will happen is, it will get repelled and it will move away. Okay, whenever I place a negatively charged body within that field, it will get attracted. It will be moving towards it. Fine. Now, when it is getting repelled away, how long or how far will it get repelled? Till it crosses the boundary. Okay. So when I say I have a positive charged body here at this place, let us name this as point P, name this as point Q. When I have a positive charged body at Q, small point charge at Q, so will it get influenced by this charged body A? Definitely not. Why? Because the electric field at this point, because of this charged body, is 0 almost. It is very much far. Okay. So this is the area, this is the boundary where we can feel the effect of the charged body A Beyond that, we will not have the effect of this charged body A. Okay. So wherever there are two charged bodies, like charged bodies nearer to each other, they will get repelled, and there is a boundary, right? On now, that means the effect of this charged body beyond this boundary is 0. If I try to move a positive charged body towards the positive charged body, a point charge I am considering here, this point charge, if I try to move it towards the charged body A, I need to do some external work. I need to apply a force, do some work on it. Okay. So, considering two charged bodies, generally charge is denoted by the letter Q. Let us assume that I have two bodies. Q1 is the charge on it. Another body Q2 is the charge on this. Both are separated by distance D. I did not write positive or negative signs on them. Okay, in general, charges. Two charged bodies separated by some distance D. So there is a force between the two charged bodies. What is the nature of the force? That will be decided by the sign on them. If both are positive, Q1 and Q2 both are positive, then they will get repelled. If both Q1 and Q2 are negative, they will get repelled. If one of them is positive, another is negative, then there is a force of attraction. Whatever may be the type of force, the nature of the force, but when I wanted to talk about the magnitude of the force, this magnitude of the force between two charged bodies is proportional to the product of the two forces. So I can say F is proportional to Q1 into Q2. Okay. Similarly, the force between them is directly proportional to square of the distance between the two, 1 by d square. Okay. So when I combine these two, what I am getting is F is proportional to Q1 Q2 by d square. This is the force between two charged bodies is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So I will combine these two, I am getting this expression. When I take away the proportionality symbol, I will get a constant. Say K is a constant, Q1 Q2 by d square. Okay. So this is called Coulomb's law of electrostatic forces. Okay. Now, out of these two charges, Q1 and Q2, if I take one charge as unit charge, okay, charge is measured in coulombs. So, if Q1 is equal to 1 coulomb, C is the symbol for coulomb, and Q2 is equal to Q, then what I can do is the same expression here, F will become K into 1 into Q by d square. I can write it as K Q by d square. So this is the force between one charged body and another unit charged body. I can say this is the force experienced by this 1 coulomb of charge because of this, which is placed at a distance d. So this force experienced on 1 coulomb of charge and placed in an electric field of the another charged body Q, will call it as electric field strength of this charge at this point, and it is denoted by the letter E. Okay, E in the uppercase. I can say this is E is equal to K into Q by d square. So this E is nothing but the electric field strength, which will denote the electric field strength due to a charged body at a distance d from it. So when I go very far, that means from the charged body Q, when I go very far, that means when d is increasing its value, so automatically what will happen is the value of E will get reduced. So the force F, the electric field strength E, both mean almost the same. The only difference between F and E is when we talk about F in general, force, it is a force between two charged bodies. But when I talk about E, it is nothing but electric field because force of attraction, force between one charged body Q and another unit positive charge. That is electric field strength. Okay. So whenever we go away at an infinite distance, there the value of E will become 0. And when I wanted to move one positive charge towards the another positively charged body, I need to do some work because both the positive charges are getting repelled. I need to do work against that force of repulsion. Okay. So